Hey there, curious minds. Welcome to the Deep Dive, your express lane to understanding the innovations that shape our world. Today, we're diving into a fascinating Nobel lecture. We're going to unpack the hidden genius behind these, tiny interfaces that literally power modern technology. Our mission here is to really get into Herbert Kroemer's 2000 Nobel lecture. It's called Quasi-Electric Fields and Band Offsets, Teaching Electrons New Tricks. We're going to explore how his work on semiconductors, and specifically this idea of heterostructures, didn't just win a Nobel Prize, it actually laid the foundation for almost all modern electronics. The smartphone in your pocket, the fiber optics for your internet.
Indeed. And what we'll see today, I think, is a great example of how fundamental physics, when you apply it with some, let's say, audacious creativity, can really change things. It can turn ideas that seemed impossible into the technology we use every single day. And it's not just about the basic materials like silicon. It's really about engineering materials right down at the atomic level, giving electrons, as Kroemer put it, entirely new tricks to get performance we'd never seen before.
Okay, let's start right there then. What exactly is a heterostructure? Why was this such a big deal?
Right. So at its core, a heterostructure is pretty simple conceptually. It's a semiconductor structure built from two or more different semiconductor materials joined together. But the really crucial insight that Kroemer highlighted is that the interface, that tiny boundary, where these different materials meet, that becomes the most important part, the active part of the device.
So it's not just the materials themselves.
Exactly. It's how they interact right at that seam. He mentions the elements involved usually come from columns the third, 4, V, and psi of the periodic table, the ones with the right electron setups for semiconductors. Silicon and germanium from column the fourth were obviously key early on. But today, many devices use highly engineered compounds like gallium arsenide, or GAs. That's a 3V material. And Kroemer really stresses that for these advanced compounds, their usefulness almost always comes down to the heterostructure properties, not just the material in isolation.
Okay, that makes sense. It's like building with different Lego bricks. But the real engineering, the clever part, is how they click together perfectly. The joint itself is where the action is. But was that easy to do? Combining different materials like that, were there immediate challenges?
Oh, absolutely. Huge challenges right from the start. One of the biggest hurdles was something called lattice constant mismatch.
Lattice constant mismatch. What does that mean exactly?
Imagine the atoms in each material are arranged in a perfect repeating grid or pattern that's the lattice. Now, for the interface to work well, electronically speaking, you need the patterns of the two different materials to line up almost perfectly where they meet, an exact match, ideally.
Okay.
But different materials naturally have slightly different spacings between their atoms. Kroemer pointed out, for instance, the mismatch between silicon and germanium. It's about 4%.
4% sounds tiny.
It does, but at the atomic scale, it's significant. That tiny difference creates a lot of strain and structural defects right at the interface, broken bonds, misaligned atoms. And those defects, they wreck the electronic properties, they make it really hard to build useful devices. So overcoming that mismatch was a massive material science problem for a long time.
Right, so the idea was there, but actually building it was the tricky part.
Precisely. It took years, decades even, of effort in developing new ways to grow these materials to get past those fundamental hurdles.
Okay, moving on from the physical structure, Kroemer introduced this really interesting idea of quasi-electric fields. This sounds key to his teaching electrons new tricks. How is this different from a regular electric field?
Yes, this is a really profound distinction, and it's central to his whole approach. A true electric field, the kind we usually think about, like from a battery, well, it basically just tilts the energy landscape, the energy bands inside the semiconductor. If you apply it, electrons, negative, and holes, which act like positive charges, just move in opposite directions, like, balls rolling downhill.
Okay, standard stuff.
Right. But Kroemer, back in a 1957 paper, came up with this concept of a quasi-electric field. Now, this is different. It's a field where the force on an electron and the force on a hole can actually be in the same direction.
The same direction? How does that work?
It's not created by an external voltage. Instead, you achieve it by carefully designing the composition of the semiconductor material itself. You make the material gradually change, say from germanium to silicon, across a region. This creates a smooth variation in the material's fundamental energy band gap, and that variation acts like an internal force, a field. He even jokingly mentioned his lemma of proven ignorance, saying if you don't get this, you can't even draw the energy diagrams correctly.
Huh. Okay.
Essentially, it gives device designers a whole new tool, a new degree of freedom, he called it. You can guide electrons internally using the material's built-in properties, not just by pushing them from the outside. Like an invisible hand, sort of?
Wow. Okay, so instead of just applying a voltage and hoping the electrons go the right way, you engineer the material itself. You create this built-in slope, this internal pathway to push them exactly where you need them. That is incredibly clever.
It really is. It fundamentally changed how people could think about designing semiconductor devices.
So we've got this brilliant idea of quasi-electric fields, this internal guidance system. How did Kroemer first use this? What was the first big practical application?
Well, the first major target was the transistor,
Mm.
specifically making a much faster transistor, the heterostructure bipolar transistor, or HBT. See, back in the mid-1950s, the early bipolar transistors, they were just too slow, especially for things like high-frequency telecommunications.
Right, they needed more speed.
Exactly. So Kroemer proposed two key design ideas using his heterostructure concepts. First, the graded gap transistor. This was the idea of varying the energy gap continuously across the base region of the transistor, like that germanium silicon example he discussed in '54. This gradual change creates that built-in quasi-electric field, a drift field, which basically sweeps the charge carriers across the base much, much faster.
Okay, speeding things up. What was the second idea?
The second, which he introduced in 1957, was the wide gap emitter. Here, the idea is to use a material with a wider energy band gap for the emitter part of the transistor compared to the base. What this does is create an energy barrier right at the emitter-base interface. It acts like a one-way valve.
A one-way valve. How so?
It makes it much harder for electrons that have been injected into the base to flow backwards into the emitter. That backward flow, or recombination, really hurts performance. By using a wide gap emitter, you suppress that backward flow dramatically. Kroemer calculated that even a small difference, like 0.2 electron volts in the band gap, could cut that unwanted leakage by a factor of, get this, 13,000.
Wow, 3,000 times better just by picking the right material for that interface. That's huge.
It's a massive improvement in efficiency and ultimately speed.
But you mentioned earlier that actually making these things, especially with germanium and silicon, was really tough because of that lattice mismatch. So these amazing HBT ideas, they didn't just take off immediately, right? They were kind of stuck for a while.
That's exactly right. You hit on a critical point. His original proposal for that GSI graded gap system, well, theoretically sound, ran into serious practical walls. He mentioned the difficulties, trying to actually grow that varying GSI alloy using the techniques they had back then. It was just incredibly hard to get the material quality needed.
So the theory was way ahead of the manufacturing tech.
Absolutely. The ideas were revolutionary, but the material science and the fabrication technology, things like molecular beam epitaxy that we use today, just weren't there yet. It really took decades for other material systems, particularly those 3V compounds like gallium arsenide and its relatives, to mature. Those materials offered better properties, sometimes better lattice matching, and eventually the technology caught up to make HBTs a commercial reality. But yeah, it was a long wait.
Okay, so HBTs eventually became reality. Now let's switch gears a bit towards light. How did these same heterostructure ideas, born from trying to make faster transistors, end up revolutionizing something totally different like lasers?
Yeah, it's a fantastic example of how fundamental concepts can cross boundaries. Here, Kroemer's insights shifted from just controlling electron flow to enabling electrons to create light efficiently. The big challenge back then was creating a semiconductor laser that could work continuously, not just in short pulses, and importantly, work at room temperature. Before heterostructures, this seemed incredibly difficult. Many people, Kroemer notes, thought continuous room temperature operation was truly impossible for semiconductor lasers.
Impossible, huh? So what was the heterostructure breakthrough for lasers?
It was the double-heterostructure, or DH, laser concept. The key idea was confinement. You take a thin layer of one semiconductor material, the active region, where light is generated, and you sandwich it between two layers of a different semiconductor material that has a wider band gap.
Okay, like trapping the light generating part?
Exactly. This structure does two crucial things. First, the wider bandgap materials act like walls, confining the electrons and holes within that thin active region. They can't easily escape. This dramatically increases their concentration. You pack them together much more densely.
And more density means?
More density means they're much more likely to recombine and emit photons, light. It makes the light generation process vastly more efficient. Second, the change in refractive index at those interfaces also helps confine the light itself, guiding it along the active layer, which helps achieve lasing. This efficient confinement is what allows you to achieve population inversion, getting more electrons into the high-energy light-emitting state than the low-energy state much more easily, which is essential for a laser to work.
I see. So trapping both the electrons and the light.
Precisely. Kroemer mentioned his early work in '68 showed promise. Low thresholds, but only impulses and at low temperatures. The real breakthrough confirmation came in 1970, when groups led by Alfarov in Russia and Hayashi at Bell Labs independently demonstrated continuous room temperature operation of DH lasers. That really opened the floodgates.
And it's just amazing to think how that concept, the DH laser, led directly to, well, everything from CD players back in the day,
Right, and DVD players, Blu-ray.
all the way to the fiber optic communication that basically runs the internet today. Our whole connected world relies on those tiny lasers.
It really does. It's a cornerstone technology.
Now, Kroemer gets a bit philosophical in his lecture, reflecting on this journey. He talks about something he calls the lemma of new technology. It sounds like it stems from the initial reaction to the DH laser. People didn't immediately see its potential.
Exactly. This part of the lecture is really insightful, I think, for anyone involved in innovation or even just observing it. He recalls how people initially dismissed the DH laser. They said it could not possibly have any practical applications. Can you imagine?
Hard to believe now.
Right. So he distilled this experience into his lemma of new technology. And it basically states this: the principal applications of any sufficiently new and innovative technology always have been and will continue to be applications created by that technology.
Created by it, not just improving existing things.
Precisely. He argues we make a huge mistake when we judge a truly new technology based only on how well it fits into existing applications or markets. That almost always leads to undervaluing it, to being short-sighted. He mentions the frustration of trying to justify the DH laser research when people were just thinking about, I don't know, better light bulbs.
Right, it wasn't just a better light bulb.
Not at all.
Yeah.
The DH laser created the need and the possibility for high-speed fiber optics, for optical data storage like CDs. Those applications didn't really exist in a meaningful way before the laser made them feasible. And he makes a really strong point. He says, what is never acceptable is an attempt to justify the research by promising credibility-stretching mythical improvements in existing applications.
That's powerful. Don't try to shoehorn a revolutionary idea into an old box just to get funding or approval.
Exactly. It's a call to recognize that true innovation often opens up entirely new fields, new possibilities we haven't even thought of yet.
That really does make you rethink how we evaluate new ideas. We're so often focused on the immediate incremental improvement, but the real breakthroughs. They change the game entirely. They create their own game.
That's the essence of it, visionary thinking.
Okay, so we've got the concepts, the devices, the philosophy, but let's circle back to the how. We touched on the difficulty, but how do you actually build these incredibly precise atomic scale structures? What were the key material science challenges beyond just the concept?
Well, as we discussed, lattice matching is absolutely paramount, getting those atomic grids to align almost perfectly at the interface. Any significant mismatch introduces strain, dislocations, broken bonds and imperfections, and these defects act like traps or scattering centers for electrons, degrading performance badly.
So finding materials that naturally fit together was crucial.
It was a huge advantage. Kroemer highlights the gallium arsenide aluminum arsenide system, GASLAS. He calls it a great crystallographic accident because their natural lattice constants are almost identical.
An accident.
A very fortunate coincidence of nature. That near-perfect match was a major reason why Janus-based heterostructures became so successful relatively early compared to, say, silicon germanium systems where the mismatch is larger. He includes tables in his lecture showing these lattice constants for various materials, and you see how tiny differences, just fractions of an angstrom, can make or break a device concept.
Okay, so perfect atomic alignment is job one. What else?
The other critical concept is band offsets. This is about how the energy levels, the energy bands of the two different materials line up relative to each other right at the interface.
How the energy levels meet, like steps.
Kind of, yeah. Imagine the energy landscape for electrons in each material. When you join them, how do those landscapes connect? Do they form a step up, a step down, a staggered arrangement? Kroemer illustrates different types: straddling, staggered, broken gap. Each type of alignment dictates how electrons and holes will behave at the interface. Will they be confined? Will they be encouraged to cross? Will they be separated?
And different alignments are good for different devices.
Exactly. For example, a certain type of staggered alignment is ideal for confining both electrons and holes in the active region of a laser, like we talked about with the DH laser. Another alignment might be better for the wide gap emitter in an HBT. So understanding and controlling these band offsets is just as critical as getting the lattice match right. And measuring them accurately was another challenge. Techniques like capacitance voltage, CV profiling, became really important in the 70s to actually map out these energy alignments.
So it's this incredible combination. You need the physical structure, the atomic alignment, to be almost perfect.
Mhm.
And you also need the electronic structure, those energy band alignments, to be just right to make the electrons and holes do what you want.
That's it precisely. It's materials engineering at a truly fundamental quantum level. You're designing the very landscape the electrons live in.
What an incredible journey we've taken today. We went from, basic physics concepts like energy bands all the way to these sophisticated devices that really define our modern world. Kroemer's work, his deep dive into teaching electrons these new tricks, it really did teach us how to build a smarter, faster, more connected planet.
Absolutely. And if you zoom out a bit, Kroemer's lecture isn't just, a history lesson in semiconductor physics. It's really a testament to the power of fundamental research, the kind of patient, deep thinking about the what and the why of how materials work at their core. Even when the applications aren't obvious right away, it shows how that foundational understanding can eventually lead to these revolutionary technologies that completely reshape society, often in ways the original researchers couldn't have fully predicted.
So, thinking about that, what does this all mean for you, our listeners? When you encounter new technologies, maybe in your own field or just reading the news, try to remember Kroemer's lemma of new technology. Don't just ask how well this new thing fits into today's world or solves today's problems. Ask yourself, maybe, what entirely new possibilities could this unlock? What applications might this technology create that we can't even imagine yet? Here's a thought to leave you with. How many potentially world-changing ideas or technologies might be getting overlooked right now simply because we're trying to judge them by the standards of the present instead of imagining the future they could create? We really hope this deep dive gave you a useful shortcut to understanding these crucial concepts and maybe sparked a bit more curiosity about the amazing hidden science that powers our world. Until next time, keep exploring.